Marina, good morning. May I welcome everyone to the Villa Marina for this morning's very special event, one I know you're all going to enjoy, and one that is going out live on the World Wide Web. Now, we should have with us this morning students from our 5 secondary schools, so if I can just check so we make sure you actually arrived, because I can't see anything. Let me just see. Ballacameen High School. Not bad. Castle Rushen High School. QE2 High School. Always noisy from Peel. Ramsey Grammar School. Not like Ramsey. Do you want to try that again? Ramsey Grammar School. St Ninian's High School. And also we're joined from students from King William's College. He's very shy. Isle of Man College and the Islands Business School. Again, a quiet one. They are here, I'm told, so anyway, welcome to all the students. Hope you're going to have an absolutely fantastic morning. Welcome to my Tynwald colleagues, and I'm sure they're going to enjoy what we're going to hear today. This is something that we're very pleased to be able to host in the Isle of Man. And I'm going to introduce our first special guest for this morning, and that is Professor Brian Cox, and he has been responsible for bringing to life the wonders of our world and the universe in a way which has made it most interesting for millions of people of all ages, and has also resulted in some spectacular television viewing, including him standing, which I only saw the other night on telly, on top of an ice mountain, where I know from an interview he did elsewhere, he was about 4 hours on that mountain while a helicopter flew around filming him, and it was a very cold day, but he says he was well wrapped up, so it wasn't too bad. His programmes were ones not to be missed, and everybody, I think, who started to watch the series on television really made sure either they recorded them and saw them later or actually stayed in to watch them. And it's really been a fantastic way that he's portrayed the development of the world and the universe. And I think it's fair to say it's been most inspiring, exciting, interesting, and above all, most enjoyable. He's introduced a whole generation to the wonders of our world and our universe. And Professor Brian Cox's talks have inspired audiences right across the globe. Interestingly, some of you may not know, Brian began his career not as a physicist, but as a rock star, when his band Dare signed a deal with AM Records in 1986. The band broke up in 1992, and then Brian joined Dream, whose song Things Can Only Get Better was famously used by Tony Blair as the Labour Party's election song of 1997. I'm not sure if he's going to sing for us tonight, but we never know, or today I should say. During Dream years, Brian Cox obtained a first-class honours degree in physics from the University of Manchester, and a PhD in high-energy particle physics in Hamburg. In 2005, he was granted a Royal Society University Research Fellowship, and in 2009 became Professor of Particles Physics at the University of Manchester. Professor Cox writes a regular science column in the Sun newspaper and has written 3 books. He has a unique ability to present science in an engaging manner, which has made him popular as a television and radio presenter. Anyway, enough from me, because what you've actually come to do is hear Brian Cox. And therefore, so let me formally welcome Professor Brian Cox to our island and thank him for taking the time to come here in what is a busy schedule. We're really delighted, Brian, to have you on the Isle of Man. We're looking forward to your presentation this morning. I know you're going to have everybody mesmerised, and I'm sure you'll have some interesting questions from the students. So may I ask you all to give a very warm Manx welcome to Professor Brian Cox, OBE.
Thank you. Just before I begin, I really do want to thank everyone on the Isle of Man. It's my first visit to the island. It will not be the last, certainly. I've had a wonderful time, an inspiring time, so thank you all. Thank you for inviting me. So for the next, hour or so, but for the next 20 minutes, I want to give you an introduction to well, big science in a way. So the two ends of the scientific project, particle physics, which is what I do at CERN in Geneva. So I want to talk about the Large Hadron Collider. But also, at the other end of the scale, cosmology, the study of the universe on the large scale, because those two different sort of disciplines, I suppose, have really come together over the past 10, 20 or 30 years to give us a quite powerful and startling view of the universe. I think if there's one thing I'd like you to take away, it's the almost hubristic nature of the scientific endeavor at these two scales, the very small and the very large, because the picture it's given us of our universe is truly, I think, remarkable. And to get some sense for how remarkable it is, how ambitious that project is, I just want to start by giving you a quick flash, a sense of the scale of the problem. So this is a picture, actually if you dim the lights a bit so you can see the astronomy pictures better. This is a picture of the night sky. If any of you are amateur astronomers, you might recognize the constellation of Orion there. But I want you to focus on a bit of sky which is about there. And it's a bit of sky that, well, there's a picture taken of that bit of sky, a very famous picture by the orbiting Hubble Space Telescope several years ago now. It's a piece of sky you would cover if you took a 5-pence piece and held it about 20 meters away, let's say. So imagine taking a 5-pence piece and holding it 20 meters away. You'd see the tiniest piece of sky. It's a piece of sky that from the ground is deliberately uninteresting. So there's nothing you can see with the naked eye. There's virtually nothing there that you can see with the ground-based telescope. It's a dull piece of sky. But the Hubble Space Telescope deliberately turned its gaze on that piece of sky for thousands and thousands of seconds, just opened its camera shutter and took a picture, probably one of the most iconic and famous pictures in the history of astronomy. You're going to hear from the shuttle astronauts who flew on the last Discovery mission later. Discovery launched the Space Telescope. It was serviced many times by the Space Shuttle. So this picture is, I suppose, the result of thousands and thousands of years of human endeavor, of manned space flight, and of ingenuity and of curiosity. Take a picture of a piece of sky that is uninteresting and see what you get. Well, this is the picture, the Hubble Deep Field image. And the first thing you see is it's anything but empty. It's anything but uninteresting. In fact, there are over 10,000 points of light in that picture. And you can see, I hope, even from the back, that they're not just points of light, there's structure there. Because these are galaxies. Virtually every point of light in this picture is a galaxy. You can perhaps see some of you see some spiral galaxies and some kind of globular and irregular galaxies. 10,000 in the picture. Each one of those points of light has, on average, I suppose, between 100 billion, perhaps anything up to 1 trillion stars like our sun in it. So 100,000 million suns in each of the 10,000 points of light in that picture. Remember, it's a 5-pence piece of sky 20 meters away. So it's, I suppose what I'm trying to say is the universe is big. The most distant object in that image, by the way, which was discovered this year, so there's still research being done on this image, is over 13,000 million light years away. So think about that. Light travels at 186,000, 300,000 kilometers a second, 186,000 miles a second. It took over 13 billion years to travel from the most distant object in that image to the Hubble Space Telescope, which is at the very edge of the observable universe. Now, imagine what that's like if you extend that over the entire sky. This is a picture, it's one of my favorite pictures. It's a galaxy map. So it's a map of the whole night sky, and every point in that map is a galaxy that we've seen, that we've observed. And you see, it's almost, well, it's impossible to resolve them all. Just to set some sense of scale, that little line there, I don't know if you can see it, there's a little line just at the top. That's the scale of the map. That's the 1 billion light year line. So this is a map of a very, very large observable universe. If you calculate how big it is now, it's something like over 90,000 million light years across. That's the bubble we can see. And you can see that the structure in there, which is fascinating in itself, the galaxies are not randomly distributed. They seem to come in strands and clusters and clumps. And remember, these are galaxies, 100 billion stars in each point. And we think, actually, that the structure there relates to events that happen happened something like a millionths of a second after the universe began. So when this entire observable universe of billions of galaxies was compressed into something no bigger than a single atom, we think that the events that seeded the formation of the galaxies and everything that we know occurred. It's right at the cutting edge of physics. I just want to give you one last number, because I'm throwing out loads of numbers here about the size of the universe. I've written it down on the top. This is the observed number of stars and galaxies in the universe, in the observable universe. It says 30,000 million stars. 30,000 million suns, 350 billion large galaxies, and 7,000 billion smaller dwarf galaxies. That's the piece of the universe we can see. And so when I said hubristic at the start, the goal of science, of big science, is to understand what all that's made of, where all that came from, how all that came to be, how it behaves, and what its future will be. So it seems like an almost impossible goal, but we can do it. So how have we been able to do it? Well, this is a picture of the origin and evolution of the universe, I suppose. The Big Bang, the current best theory we have about how the universe evolved. We know that it's, well, quite precisely, one of the most remarkable numbers, I think, in physics, 13.73 plus or minus 0.12 billion years old. So that's already a remarkable measurement. And the Hubble Deep Field image, actually, is one of the pieces of science we use to make that measurement. So 13.73 plus or minus 0.12 billion years old. So it began at that point, and it expanded and cooled. As it expanded and cooled, the stars formed, the complex galaxies form, and we get where we are today, 13.73 billion years later, with planets like Earth. An overwhelmingly complex picture. So just think about it. There are not only stars and planets and galaxies, there are things like people. There's our civilization in the universe, a structure within the universe that's evolved and crystallized out. But what we found, and this is essentially by experiment, I know of no good reason why this should be so, but what we found is as you sweep back in time, so you go back towards the Big Bang, then, well, several things happen. One is the universe shrinks, because we know our universe is expanding at the moment. The universe gets hotter, because it's getting smaller and smaller and smaller. And we found that it gets simpler. And I suppose, arguably around 100 years ago, from when Ernest Rutherford, who's a predecessor of mine at the University of Manchester, discovered the atomic nucleus, we've seen that actually when you go back in time, all the way back to the Big Bang, the universe gets very simple indeed. And so our current picture is that, I suppose, the universe, the complexity is crystallized out as the universe got older and older and older and colder and colder and colder. So complexity is a property of an old and cold universe. So an experimental approach that suggests itself, and this is what we do, it's one of the ways we try and understand the universe, is to recreate the conditions as close to the Big Bang as you can. You'd really want to build a time machine, go back and take pictures of the universe in its earliest days, but you can't do that. And when I say days, actually, that's an exaggeration. What we can do is recreate the conditions in the lab that were present less than a billionth of a second after the universe began. So you could picture it really as getting a time machine, going back to a billionth of a second after the Big Bang and taking a picture of the tiniest sphere of space, smaller than a single atom, to reveal the underlying processes that are taking place there. Why? Because everything is simple then, and the complexity masks that simplicity. So I suppose a good analogy I really like actually, is to think about a snowflake in the palm of your hand. A snowflake is a very complex and beautiful thing. Every snowflake is different. But as the heat of your hand heats the snowflake up, then it melts into a pool of water in the palm of your hand, and you see that actually that snowflake was nothing more complex than water, H2O, hydrogen and oxygen stuck together. In the same way, we found that the universe seems to behave like that. So that's why we want to recreate the conditions as close to the Big Bang as we can, and you can do it quite simply if you've got one of these, which is the biggest scientific experiment ever built. This is the Large Hadron Collider at CERN in Geneva. It's 27 kilometers in circumference. It spans 2 countries, so that's Switzerland up there, and this is France down at the bottom here. If you've ever flown to Geneva, if you've ever been skiing near Geneva, then that's Geneva Airport runway there, so you get some sense of scale for this machine. 85 countries have collaborated in building it. It's a truly